Hey there. So today I'm going to be looking at some population models. This is section 2.1. Could have sworn I had a video for this, but I cannot find it to save my life. So we've talked a little bit about exponential growth models. Looks like this. This is, by definition, a population model. It could be a population of money, a population of people, rats, what have you, rabbits to some degree. This gives the idea that it's unbounded. It's just going to take off and go up forever, which may or may not be a good approximation. For all intents and purposes, if you had, I don't know, 10 acres of I don't know, manure kind of things out there, well, for all, you could pretty much let flies do their thing forever out there, to a point anyway. Probably not going to be any total cap to the amount of flies you could have out there, any real cap. That is, it's probably going to just continue going up forever. Plenty of supplies, plenty of whatever for them to live on. Nothing to really worry about that. So this model is pretty good for some things. Other things it's terrible for. Obviously, when it comes to making money with interest in an account, this is also true. This is also true when you talk about population, when you talk about like radioactive decay. This is also the same exact model. I grew up downwind from Hanford, and they'd always talk about, what if it blew up? When can you go back, Jay? Well, never. What do you mean? Well, the half-life of that nuclear stuff that they were working with, plutonium in the one case, never. And so my grandkids couldn't go back either because I would have been sterile at age 16, and so that would have been a problem too. So, whatever. So, but radioactive decay, dropping off like that, that's exactly the same model. Now, I want to pretty much just talk about populations today. So just if you will, in your mind, think about some little critters doing their thing. They have a birth rate. So a birth rate, and your book refers to it as beta. Most books do. They also have a death rate. And provided that the birth rate is greater than the death rate, which they use delta for death rate. If it's greater than the death rate, then B minus delta will be positive, right? Beta minus delta will be positive. And we'll call this K. Okay, we'll also call it K when it's not true, when beta is less than delta. And if that's true, then, of course, this is less than 0, in which case you'll get decay. Specifically, I want to talk about this case here. Okay, but think about this for a minute. So the birth rate is a percentage of the population. So let's say that our percentage of the population is something like 1/10 of the population. Now, if I take that and then I subtract the death rate, let's say I'm losing 7% of the population every year, what I'm ending up with is a 3% gain, if you will. Oops, what am I doing times B, you idiot? There. Try it again, Jay. Idiot. There we go. I swear I know what I'm doing. I know what I'm doing. Trust me, I know what I'm doing. We end up with a 3% gain in the population. Okay, and that's how that thing comes about. Remember, these guys here are a rate, but it's a rate. It's a percentage of what you had currently. So like this year, let's say initially at x equals 0, I had nice easy 1,000 people in the population. Okay. Well, I'm expecting to gain 100 people this year. I'm expecting to lose 70 people this year. I'm going to gain 30 people total this year. That's my expected value. Now, obviously, it might be a skosh more or a skosh less than that. So 7% of 1,030. I need a calculator. I can't do math today. Obviously, it's going to be a bit more than 70, and not that this is really hard. And if I really cared to do this, why? What did I say? Yeah, well, duh, 103 people. I don't know why that was so hard for me. 0.07. Good. So this minus that. I expect to gain 30.9 people. So again, this is an approximate value, 160.9. And you play the game again and again and again. Okay? But obviously, we added 30 this year. We're going to add 30.9 this year, but in each case it's 30% of the previous amount. That's a big deal because it's always proportional to that original amount, or toward the or proportional to the population. Frequently, in fact, what they'll say is that the change is proportional to the population. That is a exponential growth model, or decay, either one. It's proportional. We make it equal by multiplying by some constant. So there it is. Okay. Again, this is separable. So if you tell me that its initial population is 100 and this is 0.3, then I will, or 0.3, then I will tell you that 1 over x dx is equal to 0.3 dt integrate ln of x is equal to 0.3 t plus a constant, exponentiate, and you get x equals c e to the 0.3 t. When x is 0, when t is 0, x is 100. That means c must be 100, and voila, there you go. Okay, so that's interesting. That's pretty neato, I guess. Interestingly enough, the next model, which we've already talked about a little bit, is the logistic growth model. And what it says is that the rate of growth is proportional to two things. In fact, this time is proportional to well, it can be read several ways. I should put it that way. It can be read several ways. And so so one way to say it is it's proportional to the population itself and the difference from the carrying capacity. So m minus x. And that's one of a couple of ways to write it. Okay, and that's pretty good and all. The problem with that is when you go there, you're like, well, I get it, but where is this m coming from? And so a better way to look at it is, in fact, to look at it like this. And so keep in mind that initially what happens in any population. In any population, you have some initial birth rate. Okay? What happens is your population grows. Okay? Well, as our forefathers in this country used to have routinely 8, 9, 7, 14 kids, whatever. My grandma had 14 brothers and sisters that lived to grow up. Okay? That's nuts to even consider thinking about that. All right? It absolutely boggles my mind. My grandpa only had 2, but that's because his dad was like 60 when he got married the first time. So I think that had something to do, or 50, 55, 50, 50, 50, I think, when he got married the first. That was like when he first got married. So he didn't really have a whole lot of time to have a lot of kids. Plus, I'm guessing at my age, which I'm not 50 yet, but I'm guessing at my age, I don't think I really want to have a bunch of little babies running around the house. That's got to be crazy. So what's going to happen over time is we'd expect that birth rate to decline. Does that make sense? And it's going to decline in proportion to the actual population. Okay, so in other words, it started at some initial B naught, and then it's going to go down, but it's going to go down as this baby goes up. As this population goes up, the birth rate is going to go down. Does that make sense? So I think that's kind of a big deal. And then of course, to that, of course, oopsie daisy, I almost forgot about that. So you're going to have minus an initial death rate. Now that's kind of how, if you were thinking about this before, we had beta naught. What we were doing before was beta naught minus a delta naught, if you will, times x. Okay, so what this right here is, this part right here really becomes, well, this is very similar to what we were talking about before. In other words, this looks a lot like this, except obviously this rate here changes as the population goes up. Delta may or may not go up as the population goes up. In fact, you might see delta actually drop, because as time's gone on, our death rate has gone down because we're not having such a high child mortality rate and that sort of thing. But for right now, we're going to leave that alone. And so we're going to multiply this, you see, by x, just like we did before. This right here was our k before, but notice it's a constant. It's not a constant anymore. It too varies as time goes on. And so what we're going to see is this. I can rewrite this a little bit as beta naught minus delta naught, all right, times x. I'm just going to rearrange those two and put them together first, and then I'm going to distribute, okay? And then minus beta 1 x squared. That pretty neat, like that? I feel like that works. And so what you can end up doing is if you're careful of this deal here, is you can rewrite this thing in such a fashion, like for instance, you factor an x out. Okay, well, we had the x factored out. I'm sorry. So we have this situation here. You're like, oh, look, it's quadratic. It is quadratic. So two things occur to me. In the video this week, we'll be talking about equilibrium. So there will be two places where this guy equals 0. So that's one thing that occurs to me. The other thing that occurs to me is if you transform this ever so slightly, you will get beta naught minus delta naught, like I said, minus beta 1 x times x. Does that make sense? So then what a person could do then is continue this path a little bit. Let's factor a beta 1 out. So you factor a beta 1 out, and you're going to get beta naught minus delta naught over beta 1 minus x times x. And of course, if you bring that down here, it becomes beta 1x, and then beta naught minus delta naught over beta 1 minus x. Hey, that looks an awful lot like kx m minus x. And that's in fact where that carrying capacity, or this m, comes into play. Okay. I'm going to do a couple of these like I did last week in class, just to say that we did them. This is how you do them. Again, remembering that this isn't terribly hard. You may use a calculator for this integration. I don't really want to overthink it too much. But if you were to do this by hand, trying to impress somebody, alright, you're going to integrate, you're going to separate and integrate. I'm going to leave the 0.02 over here because I can. This is 0.02 t plus a constant. On this side, I'm going to have 1 over this mess. I'm going to use partial fractions, a over x plus b over 200 minus x. Okay. If you multiply by that common denominator, you get 1 equals a 200 minus x plus bx. And again, there's the two ways to do it. You can plug in the two equilibrium solutions, or which is when x is 0 and when x is 200. It's probably the easiest in this particular case. So if x is 0, you get 1 equals 200a, which means a is 200. I'm sorry, 1/200th. I'm sorry. And if you let b equal, or if you let x equal 200, this goes to 0. This becomes 200b is equal to 1. So b is also 1/200th. So now what you need to do is you integrate 1/200th, 1 over x dx, plus 1/200th, 1 over 200 minus x dx. Well, this is 1/200th ln of x, plus, now this is your u. If you let u equal 200 minus x, you get du is negative dx. So I have a negative of a du, so this is minus 1/200th ln of 200 minus x. This will be the same basic problem every time. Okay, equals, and what did I say was equal to? 0.2, I think. Yeah, 0.02 t plus a constant. Alright, if you multiply both sides by 200, 200 times 0.02 should be 4, isn't it? Yes, good for me. 4t plus a constant. If you exponentiate, you get c e to the 4t on this side, x 200 minus x. If you multiply across, you're going to get 200. I'm going to leave it as 200c for a second so you can see that, minus cx e to the 4t. Okay. Whether you leave the 200 here or not, it's neither here nor there to me. I'm going to do it this time, I think, because it's going to make my life, it's going to make the problem a little nicer in a minute. But you do you. If you don't screw it up, it'll work either way. Oops, e to the 4t. There's a c in there somewhere. Ha! Found it. And again, this becomes the same every time. And so if you divide by that, okay, that is my, there's not an x there, you clown. There you go. That's what you end up with. Okay? And technically that's not wrong, but we typically divide by c e to the 4t everywhere. And so you'll end up with x equals 200, which is your carrying capacity. Of course, this becomes 1 plus, and then this becomes 1 over c, which is a c, but it's the opposite of the c you wanted, or you thought you had. And then e to the minus 4t. That's your answer. Okay? So if x naught was equal to 10, let's say, okay, well then what would have to happen? Well, when x is 0, this would be 1 right here, right? Well, if that's 1, then 1 plus something, and when you divide it into that, you're going to get 10. So c is obviously 19, I think. Is that right? You buy that? And so there it is. Look at it is one you'll see like this. Something like 0.02 t, or x rather, sorry. And then times something like this, but watch carefully, x minus 10. Oh, that's crazy. Notice that our equilibriums, again, which you'll talk about later today, obviously in our next video, are at 0 and 10. They're the values that make this thing not change. Interesting, though. What happens when x is between, here's x equals 0, here's x equals 10. Remember, those are functioning like quote-unquote y values. When x is 0, of course, there's nothing happening. When x is negative, this is negative, this is negative. This looks like it'll be positive slopes down here. When x is when x is like 5 or something, this is positive, this is negative. We're going to get negative slopes in here. Okay? And what happens when x is bigger than 10? Well, positive, positive. Ooh, interesting. So because these are population models, we don't really pay attention to these ones down here. But what happens? If you get off of 10, it's either going to collapse or it's going to take off. What this is sometimes referred to as explosion extinction. Also sometimes referred to as a doomsday scenario. Okay? And so we're going to solve this, and you're going to see why. Well, it's pretty obvious why it's a doomsday scenario when things take off and go nuts. The formula is exactly the same as you think it would be in terms of it's still separable. This side is still the same as last time. This is going to be, boy, what is that going to be? It's going to be 1 over x minus 10 equals a over x plus b over x minus 10. So it's going to look something like this plus this. If you let x equal 0, you get, interesting. So a is, so you're going to get negative 10a equals 1, which means that a is equal to negative 1/10. And if you let b equal, or x equal 10, then you get that b is equal to 1/10. That's correct. And so if you integrate that, you're going to get the ln, what does that say? The ln of x, but it's negative 1/10 of that, plus 1/10 ln of x minus 10. Interesting. Notice that they're backwards this time. Still subtraction, but the other one's on top this time. So it's going to be 1/10 ln of x minus 10 over x. Careful. 0.10 2t plus c. Was it 0.2 or 0.02? 0.02. Okay, exponentiate or times both sides by 10, and you should get 2t plus a constant, and then x minus 10 over 10. I'm sorry. If you multiply both sides by 10, and then this is still in an ln, and then if you exponentiate, you will get c e to the 2t. And so x minus 10 equals cx e to the 2t. If you subtract this over there and play musical chairs, you'll end up with 1 minus cx e to the 2t is equal to 10. 1 minus cx e to the 2t. That right there is your answer. And so let's say that x naught was equal to 5, for instance. So then x equals, and then it's going to be 10, 1 minus c, oh, there's no x there, you idiot. 1 minus c e to the 2t, and if you let 5 go here, right, then you're going to get, and this goes to 0 then, 1 rather, I mean. So you're going to get 1 minus c equals 10 over 5. 1 minus c equals 2. C then is equal to negative 1. Is that correct? So then this should be something just went screwy. I was freaking myself out. That would be correct if x naught was 5. Let's pick an x naught that's a little bigger than 10, just to see what would happen here. So clearly, what's going to happen this way here is we're not wrong. But what's going to happen is t gets bigger. What's going to happen to this denominator? It's going to get huge, and the whole population is going to go to 0. That's literally what was supposed to happen. For some unknown reason, Jay was having a hard time fathoming that because, well, yeah, not too bright sometimes, I don't think. Anywho, if it were actually 12, then you would get this. And then if you did the math on that, you would get it's 1 minus 5/6. It equals 6. Or c, rather, so c is 1/6. So your model would become this. Geez, I don't know why it was taking me so long to grasp that concept this morning. I'm sitting there going, I know what I'm supposed to be doing. Now, what happens is t gets big. This whole thing goes to infinity. I'm sorry, this whole thing takes off and goes. What's happening here? I'm sorry. Yes, as t goes to infinity, you're like, oh, this is going to go to this is going to be in, a fairly large negative number. But that's not the gist of the problem, friends. Look at this fraction. Oops, look at that fraction. What can never happen? We can never have a denominator that's equal to 0. You see that? But there is a time when that will happen. On the previous problem, that denominator would never be 0. But here, in fact, time could equal 0. Or not time could equal 0, the denominator could equal 0. So, but the time when that happens would be, well, 1 minus 1/6 e to the 2t would have to equal 0. In other words, 6 would have to equal e to the 2t. Is that correct? And so then if you take the ln of 6, divide by 2, that would be your answer for t. When that happens, that's what we call doomsday. That's when the time occurs. I can't leave well enough alone. I need to know what that is. So the ln of 6 by 2. Good one. So at about 0.895 time units, if that's seconds, by the time you figure that out, you're screwed. If it's years, it still doesn't take very long. You got about 9 months to get that figured out, and then once you figure it out, you got to do something about it. So again, good luck with that. Millennia, you know, you'll be dead, so I guess don't worry about it. But that's the explosion extinction model, and there's really not a whole lot of difference in them in terms of how they do it, except where it comes out in the end. You know, why would that come back to that? Why would that come back up to here? Why would that end up being positive or negative? Why would this be positive and that be negative? Well, let's think what would happen here. Back to our original model, which oops, no, there it was. I found it. There it is. Cool. If you come back to this original model, what are we saying here? Well, we would like this bit here to be positive, yes? Well, how is that going to be positive? Well, if your birth rate, instead of going down as the population grows, like right there, if it instead went up as the population grows, okay, that would give us the positive value that we seek, because remember, it has to end up being something like ax plus x squared, or plus bx squared, something along those lines. That is what the explosion extinction model looks like. That is, beta naught still has to be bigger than delta naught, and that needs to be positive for that to happen. Again, it's one of those models that shows up occasionally. It's kind of fun. It's kind of neat to work with. Kind of fun to work through the thing. I'm going to show you one cool thing right now. We're going to experiment more with it later on. I'm just going to introduce it today just to see what you think of it. And I'm going to use numbers that make no sense in terms of modeling, but make sense for selling the bit, if that makes sense at all. So these numbers make no sense in terms of a model. Can you give me an example, Jay, where they have that? No, I can't. I only use this one so that it's easy to see the point I want to drive home. This is the only reason. Like, wait, what is that, Jay? Oops, is it minus 7? Yes, minus 7. I think I want minus 7. Yeah. And you're like, wait, that's weird. Why are you doing that? Well, what if you had a population and you harvested some stuff out of it? What if you harvested some stuff out of it? It's like some fish in a pond, and you harvested a certain amount every year. Like you worked for the government, the state government, and you decided that you could fish this many millions or thousands or whatever of fish out of this lake every year. Okay? Well, something that occurs to me is I don't want my fish population to grow like unbounded. I mean, they won't, because they will run out of resources. But I would like them to grow and be healthy in there. And then, but also, I wouldn't want them to go to nothing either. So I don't want to overfish them. So there's like a sweet spot in there where you could factor out, again, this is a constant amount, 7,000, 7 million, whatever it happens to be. Or maybe just 7 fish. That seems weird, though. So an interesting thing is we're going to actually set these guys equal to 0. And we're going to talk about this later on. And so, but I introduced it now because I want you to kind of keep that in the back of your head as we go along. If you did this, I'm going to change this up so it looks more like we're used to seeing. God dang it. Should have made that minus 5. I'm doing this off the cuff. It just hit me right before I did this. I was like, I want to show these people this. Yeah, let's say minus 5. A minus 7 would have worked, but it would have been weird and it wouldn't have factored. Yeah, I want to factor nicely. If you were in Algebra 2, of course, what would you do? You'd do this and you'd go, oh, I know, let's factor it. Ooh. And yeah, look at that. So it says my equilibriums are when there's this many, like one, let's say that x equals 5 is 1,000. There's 5,000. So x equals 1 would be 1,000 fish, equals x equals 5 would be 5,000 fish, x equals 6,000 fish. So instead of like having 0 fish in a pond, if you had no fish in the pond, well, you can't take fish out of it. You would have to have a minimum of 1,000 fish in the pond, and somewhere between 5,000 and 1,000 fish in the pond. And what's going to happen if you're in there? What we're going to see is it's going to still be logistic growth, and we're going to explore this quite a bit later on, like that. If you stay between 1,000 and 5,000 fish. If you get too many fish, what's going to happen? Well, if you had like, we'd have to be careful. Oh, so we factored this, and we moved that negative over there. Be careful when you're doing that in differential equations, because in reality, that negative is still here on this side. So if x were bigger than 5, these guys would both be positive, but that negative we factored out would still be here. We'd have a negative growth up here. That happens to a lot of people who are very good at algebra. It happens. It's happened to me many times where I'm like buzzing along. Hey, I'll just multiply 3 by the negative. Ooh, yes, but you're still setting a rate equal to 0. Well, and that's interesting. I want to note that rate to equal 0, and that's great. That's when it equals 0 are those 5 and 1s, and whether it's up or down makes no difference at those 2 points. However, I want the true meaning of it. So instead of multiplying through by that negative, what I should have done is just put it like that. So I know it's going to come down to this value, and of course down here it's going to drop off. In fact, a 0 is never going to go less than 0, even though the model might suggest that it cannot go less than 0 fish. Obviously, it's fish in a pond. And what we're going to see is that, you know, Jay, this is fine. You could, in fact, fish that many fish out and be okay. What if you raise this up to 10? Just think about this. Now, this is not part of the assignment today, but just think about that for a minute. Well, I said equal to 0. Sure. Can you factor that? You can't factor it. But I bet you could do the... I'm going to rewrite it. Well, here, I'm just going to put the 10 here, if that's okay with you. I am going to use the quadratic formula. So negative 6 plus or minus the square root of 36 minus 4 times a times c. It's going to be minus 40 over negative... Uh-oh. Say, can you fish this many fish out? And the answer is no, you can't. And so what happens when you do that? Well, it means that there is no equilibrium. If you take that many fish out, what's going to happen? It is going to drop to 0. You will fish all the fish out of this lake. There's no equilibrium. There's no place where it'll stay and be at a certain particular level. That's a big deal coming up later on. And that is how, in theory, biologists decide how many fish to take out of a river or an ecosystem like that, or hunting deer, whatever it happens to be. They take a lot of that into play, and they try to come up with a spot where you can get a pretty steady state population out there. We don't want populations exploding. We don't want them to go away either. We would like them to be a healthy population. So, well, again, we're going to spend a whole unit later on talking about that. I think it's interesting to bring it up now because you're like, okay, we're talking about equilibriums. That's cool. We're talking about this growth model, this population model. Well, that seems pretty easy to do. So from right here, that's a classic case that we see pretty much every day around us. And so just kind of keep that in mind as we go along. We'll talk about much more about it when we get there.